you take it away?
Sure. Hello, everyone. I am Qijia Shao, a last year PhD student at Columbia University working with Professor Zhou. Today, very happy to talk about our work in Neural Predictor. This work was done during my internship at Snap Research, working with my colleagues Jian, Bing, Wu, Guru, and Shree. So a neural is a predictor designed to simultaneously reduce jitter and lag in human display interactions. And let's take a simple example here. It demonstrates the overlay of the detected face landmarks on a user. And from the left, you will notice a slight mismatch between the landmarks and the user. And this discrepancy arises from the delay in detection and rendering. And when we look at this static frame, both of the double exponential filter in the middle and a neural on the right have effectively compensated this delay. So they have better alignment. And through the video, the jitter effects become more evident. And you can see only the neural predictor managed to tackle both jitter and lag. So the motivation of this work is that interacting with displays like TV, smartphones, and AR/VR headsets is becoming a popular way for us to process information in daily lives. And many of them are hands-free. And in those hands-free systems, a camera is usually used to track the user by processing low-quality images, which introduces jitter. And the processes like exposure, tracking, and rendering all introduces lag. In other words, when the tracking is done and the rendering finishes shows on the display, the user could already move to another location. So for the best user experience, we want to make a smooth prediction to reduce jitter and lag. Traditional predictors inevitably face the jitter-lag trade-off, while we like to achieve both smoothing and prediction at the same time. And drawing the inspiration from NB's paper, we introduced a neural predictor. It's a lightweight neural network-based predictor leverage residual learning and can be deployed on mobile devices like smartphones. And the high-level idea of a neural filter is that given a tracked human motion, we abstract it into a single trajectory, and we feed it into the neural networks. And through the first module, it will learn the general moving trend like the speed or direction out, and generate the first partial output. And subsequent module will receive this residual information from the previous stage. Then the seasonality module processes this residual to identify and learn the periodic movement patterns, such as popping during walking, and generate another partial forecast. And the final prediction is a combination of the two partial forecasts. And the predicted trajectory is both accurate and smooth. To validate the effectiveness of our neural predictor, we built a digital window system applying different filters. The digital window is designed to mimic the viewing experience of a real window. It mainly consists of two cameras and one screen. The cameras track the raw locations of the user, and the screen renders the scene correspondingly. After adding different filters to the raw tracked signal, the final user experience is improved to different levels. And when the user remains stationary, it's evident that the double exponential filter on the left exhibits more jitter compared to our neural on the right. And compared to one neural filter, which is a very widely deployed smoothing filter, the neural predictor has a comparable level of smoothness. However, the one neural filter has more lag. This distinction is more pronounced when we move and stop at the same time. And we then compare the predicted trajectories with the ground truth. On the left, the x-axis is time, and y-axis is position. And first is the ground truth, which is the shift to the raw signal, following by the LSTM prediction and double exponential prediction. Both provide decent predictions, but also amplify the jitter. And the one neural filter excels in smoothing, but at the cost of significant lag. And a neural stands out by reducing both jitter and lag. And if we look at the arrow, a neural predictor achieves the least mean absolute error in both location and acceleration. And different moving speed will influence the prediction result, especially at the direction changing point. So at slower speed, the double exponential filter, when fine-tuned with optimal hyperparameter search, performed similarly with the neural predictor. However, as speed increases, despite the hyperparameter optimization, double exponential filter cannot maintain its performance, especially at the direction changing point, and the neural predictor outperform it significantly. And to validate the neuro's actual real-world effectiveness, we conducted a user study with 34 participants in both VR and AR settings. In these studies, participants interacted with the same system, but each time optimized with a different version of filter. And then they rate their experience based on lag, jitter, and the overall experience they feel. Here, the x-axis are the three metrics I just mentioned. Y-axis is the average rating. And from the plot, we can see our neural brings the most favorable experience on reducing jitter and lag, and it received the highest score on the overall user experience. And one interesting observation is that the overall experience aligns better with the jitter performance for VR, but correlates more with the lag performance in AR. And this suggests that users prioritize smoothness in VR more, but responsiveness more in AR. And with its validated effectiveness and usability, we expect a neural predictor to bring a better user experience to various vision-based interactive systems. For example, in mixed reality applications, when our perception of the real world is instantaneous with no delay, accurate prediction becomes very important to ensure a seamless and immersive user experience. And in the high mobility tracking, proper prediction could boost the tracking frame rate. Here, we showcase an example of a neural predictor to help maintain a constant laser link between the base station and a very fast moving object. In this case, it's a drone. And it can also be any arbitrary moving object, like a ball. You can just throw the ball to your friend, and with a neural predictor, it can help boost the tracking and track the arbitrary movements instantaneously and accurately. Okay, lastly, I want to talk about some of the limitations and potential future directions. First, as one might expect, the predictor's performance dropped at turning points. This is kind of inevitable due to the uncertainty of human movement. But higher frame rate could, of course, help. So one potential solution is to employ some smart upsampling network in the first. And second is, currently when we're dealing with the non-rigid bodies, we just treat them as separate points, which overlooks the intrinsic relationship between those points, right? So we think method that could leverage, for example, shape or kinematic constraint into the prediction mechanism could do a holistic prediction better. And in our current user study, we lean on the participants' perception of lag and jitter as a reflection of the user experience. This, of course, reflect their experience, but we think a more objective motion-to-photon latency measurement would reflect this effect better. And the last point I want to go through is the current model is relatively generalizable to different motions. You can see we have human motion, drone motion, ball motion, but for each types of the motion, we do need some training data of this type, because the motion dynamics are very different. For example, the speed and acceleration for human and a machine is quite different. So we think how we can hard code some portion of this prior knowledge into the network could really help to make sure that the pre-trained network can be really useful to various applications. And this is especially helpful in practice. And those concludes my talk. And for more details, please refer to our paper, and happy to take any questions. Thank you.
You guys were so good at doing questions earlier. We'll need you guys to be just as good during the panel session. But maybe I'll ask, what's the computational resources? Is this something we can get on an iPhone, or is this desktop only?
Yes, this can be deployed on mobile devices,
okay,
like your phone. Because I think currently, actually, they're trying to deploy this on your Snapchat app.
Okay.